All right, everyone, let's get started. Welcome to the second lecture of CS285. Today we're going to talk about the first algorithm that we'll learn about for decision making and control, which is going to be behavioral cloning and also variants on it like Dagger. So these are going to be imitation learning algorithms. So in today's lecture, what we're going to do is we're going to kind of take a journey from the kind of supervised learning techniques that hopefully all of you are familiar with from your machine learning course into the most basic methods that we could use to actually learn controllers and policies that can control autonomous agents. But before we get into that, a few class notes, a few logistics. So homework 1 is going to be out probably late this evening, maybe early tomorrow morning, but probably late this evening. You'll have a couple weeks to do homework 1. Please make sure to start our homework 1 early, especially if you're not kind of completely solid on your TensorFlow and neural network training background. So if you're not sure whether you're really quite up to scratch on deep learning, give homework 1 a shot early on. Next week, on Monday, Kelvin Shu, who's a teaching assistant in the class, will actually give a tutorial on TensorFlow. So good idea to try out homework 1 before that so that when you go to Kelvin's tutorial, you'll be ready to ask questions. So on Monday next week, during lecture, I won't be giving a regular lecture, but we'll have a tutorial on TensorFlow from Kelvin. Remember to start forming final project groups. So we've already posted the final project assignment on the course website. Don't worry, it's not due yet. That's just so that you know what the final project assignment is. However, an important milestone for you is that September 25th, which is quite soon, September 25th is the due date for the project proposal. The project proposal is pretty straightforward. It's not very long. And it's really there for your benefit. So it's there for you to tell us what project you're thinking of doing and for us to provide feedback. So the course staff will give you feedback on your project proposal, and also your peers will give you feedback on the project proposal. So we will actually have a system set up where you will submit your project proposal. You'll have anonymous reviewers review your project proposal, who will be your classmates, and they will tell you whether you're passing the class or not. I'm just kidding. They'll tell you some suggestions about how you could improve your project proposal. And that's very important because selecting the right problem to work on is one of the most important parts of doing research. So please make sure to really take the proposal seriously, write out in sufficient detail what you're thinking of working on, and then receive and incorporate the feedback that you'll get. All right, so that's, and actually one more note about class logistics. For enrollment, for folks who are not yet enrolled in the class, we've gone through the wait list over the weekend, and at this point we should have emailed everybody who had filled out the Google form for enrollment. So basically there were sort of 3 emails that went out. Either you're going to be enrolled, or you're too far on the list and you're definitely not getting enrolled, or you're somewhere in the middle, in which case things will probably resolve themselves in the next couple of weeks. So if you did not receive an email like that, but you were expecting something, please contact the course staff. We have a course staff mailing list. And that's for everybody who filled out the Google form. If you didn't fill out the Google form and you're not enrolled in the class, then unfortunately the period is over for that, so that there's nothing we can do there. But if you filled out the Google form, then you will have received an email from us. All right, today's lecture. And for the remainder of this lecture and all future lectures that I'll give, please do feel free to raise your hand to ask questions. This really works best when it's more of an interactive process. The first lecture was sort of a little bit more of a performance. From now on out, it's going to be actual learning material. So to best facilitate your learning, definitely make sure to ask questions if something is unclear. If something is unclear to you, chances are it's also unclear to many other people in the audience. And I will prompt you guys occasionally to ask questions or to answer some of my questions. Okay, so here's what we're going to do today. Today we're going to define sequential decision-making problems. So sequential decision-making is right there in the title of the course. But we need to define what the heck it is so that we can start working on it. And then we're going to talk about imitation learning. So imitation learning, you can kind of think of it as supervised learning for decision-making. It's where you get data of somebody doing good decision-making, and you're going to try to emulate them. We're going to talk about whether imitation learning actually works if done in the most obvious way. We're going to talk about how you can make it work more often. Some ways to make it work more often are very principled. Some of them are less principled, but work better. So you'll see this theme come up again and again as we talk about deep RL. Sometimes there's a principled solution, And sometimes there's a solution that works, and the two are not always the same. We're going to do a little bit of theory. We're probably going to do that in the second half of the course. And it'll be a little bit of theory about imitational learning, but we'll also learn about some theoretical tools that will come up again in the future when we talk about reinforcement learning as well. And then we'll cover some case studies of recent work in deep imitational learning, watch some cool videos, and find out a little bit about what cutting-edge research in this field is actually doing. All right. The goals for today's lecture will be to understand definitions and notation, and these definitions, of course, we'll keep using again and again throughout the course. Understand basic imitation learning algorithms, and then understand some of the tools for theoretical analysis, both for imitation learning and later on for RL methods. All right, let's start with some terminology and some notation. So let's say that I'd like to build an image classifier. So I've got my image, here it is, it's this tiger, and we've got some classes, so maybe we need to figure out, is it a tiger cat, a jaguar, a lynx, or a school bus, or a bicycle, or whatever. And we'd like to train a model to do this. So it's a deep RL course, so we're going to have a deep model, and it's some deep ConvNet model right here. And we're going to attach some symbols to these things so that we can refer to them. So we're going to call the image, instead of calling it I for image, we're actually going to call it O for observation. And we're going to call the output A for action. You can kind of think of this label as the action that your classifier takes. The classifier takes the action of guessing that it's a tiger, or the action of guessing that it's a lynx, or something like that. And then we'll call this thing in the middle pi, and pi is a distribution over actions given the observation. So when you train a classifier with like a cross entropy loss and a softmax layer at the top, what you're really doing is you're training a categorical probability distribution over the output A, condition on the input O. We'll call this distribution pi, and we'll use a subscript theta. Theta here denotes the parameters of the model. So in a deep neural net, the parameters are the weights in the neural network, the weights in all the conv layers and the weights in the fully connected layers. Okay, so standard supervised learning, we've just changed the symbols around a little bit. And now, to make it clear that we're going to be in a sequential decision-making process, we'll also put subscripts t on everything. So we'll say this is the observation you observe at time step t, this is the action you emit at time step t. So if you're an image classifier, maybe you're going to be asked to classify 1,000 images in a row, so you have O1, O2, O3, etc. But of course, in a more interesting sequential decision-making process, there's an additional dependency between O and A that is not present in standard supervised learning problems, which is that the action you take actually affects the next observation that you see. So if you're just classifying images on the internet and your goal is to just classify all 1,000 images correctly, maybe the label you emit for image 1 doesn't actually change image 2. But if you're actually exploring the jungle and you actually see an image like that, then your failure to properly classify this as a tiger as opposed to a school bus or bicycle will affect, perhaps adversely, what you see on the next time step, right? Because if you don't recognize that it's the tiger, you might do something undesirable. And of course, typically your action will not be to actually classify what's in the picture, but to actually take some action. So similar principle, you might have a categorical distribution over potential actions you might take. And here, of course, you might guess that, okay, if this is actually a tiger, maybe you want action 1 and not like action 3 or something. And then you might get a more desirable image at the second time step. And of course, actions don't have to be discrete. You could also have continuous actions. So you might, for example, have the direction that you want to run when you see that picture. And in that case, you simply have to pick a parametric distribution class for A given O. So for continuous actions, a very popular choice is to use multivariate normal distributions, which means that your neural net would emit the mean and covariance of a normal distribution over A. So that could be one choice. It's not the only choice, and we'll discuss some other choices later on in today's lecture. Does anybody have any questions so far? Okay. So let's recap some of our terminology. So we're going to use O subscript t to denote the observation, A subscript t to denote the action. So the action is what your policy is outputting. And this pi thing, that's what we're going to call the policy. So in the most general setting, the policy is a conditional distribution over actions, conditional on observations. But there are a few interesting special cases of this more general setting. So sometimes you might have a deterministic policy. You can think of a deterministic policy as simply a conditional distribution that outputs a Dirac delta over just a single action. So one action has probability 1, everything else has probability 0. That's also very possible. Sometimes you will also have settings where you have policies that depend not on observations, but on something we call states. So this is a new concept that I'll introduce, although many of you might have heard about it. So sometimes you see people talk about states, and sometimes they talk about observations. So you can just as well have a policy that depends on states rather than observations, but what the heck is the difference between these things? So here's the difference. An observation is something that you see. So if you're out in the savannah, there's sort of a kind of an animal theme to all these slides, and you see this picture, you're not, it's not like you're directly told, oh, there's a cheetah and a gazelle. Now, what you really see is you see image pixels. So those image pixels are your observation. But those image pixels are produced by some kind of underlying physical process. And that underlying physical process has a state. So maybe the state here is the position and velocity of the cheetah and the position and velocity of the gazelle. You can choose different levels of abstraction. Maybe it's the state of all the muscles in the cheetah's body or something, but there's some kind of underlying state that gives rise to these observations. And the important distinction between states and observations is that the states fully describe everything that's going on in the world, whereas the observations may contain aliasing, meaning that you might have two observations that are perhaps indistinguishable to you, but that actually correspond to different states. One very simple example of how this could happen is, let's say that there's a car that drives in front of the cheetah. Okay, maybe this is a weird place for a car to be driving around, but let's say that a car drives in front of the cheetah and it blocks the cheetah, and you can't see the cheetah behind the car. The cheetah is still there, so if you actually knew the full state of the system, you'd know that there's the cheetah behind this car, but the observation may be insufficient for you to actually infer that. And this is why we sometimes refer to this setting, the A given S, as fully observed, meaning you get the state, which means you observe everything, and this setting A given O as partially observed, which means that in general there may be cases where the entire state of the world cannot be inferred from the observation. That doesn't mean that you always can't infer the full state. So partially observed means that it is possible for you to not be able to infer the full state. This distinction will become more important later on. When we talk about imitation learning, actually, very often it doesn't matter very much, but later on when we talk about things like dynamic programming, it becomes much more important whether you are in a fully observed or partially observed regime. Okay, now let's try to make the distinction between states and observations a little bit more formal mathematically. So formally, the way that we can understand the distinction between states and observations is by drawing a probabilistic graphical model that describes how all three of these things relate to one another. So in sequential decision-making problems, we assume that the underlying system has the structure of a Markov chain, and it's Markovian on the state S. So if you look at this graphical model, there are a few things that you can try to figure out from it. One of the things you can try to figure out is where is the policy? Well, the policy, at least the partially observed one, is A given O, so the policy describes this edge right here. That's pretty straightforward. And then you have your transition probabilities, sometimes also referred to as dynamics, which describe the probability of entering the next state, st plus 1, given the current state, st, and the current action, at. And just from looking at the structure of this probabilistic graphical model, if you remember how to derive independence relationships or how to do d-separation, then you can probably guess at this point that an interesting property of the states is that the state S3 is conditionally independent of S1 given S2. Right? So if you know the present, then the future is conditionally independent of the past. If you know the current state, nothing about past states matters as far as guessing future states. So this is called the Markov property. So the states form a Markov chain. If you don't observe the states and you only look at the observations, they do not form a Markov chain. So if you didn't know S1, S2, and S3, then O3 is not conditionally independent of O1 given O2. If you think back to the example with the cheetah and the car, if you see the cheetah, and then the car drives in front of the cheetah, now you just see the car, you don't see the cheetah. If you want to guess what you'll see at the next time step, the current image doesn't tell you everything, but the previous one does. So if O2 is car in front of cheetah, O1 is the car is not yet in front of cheetah, and O3 is what you're trying to predict, for example, then knowing that in O1 you saw a cheetah is actually important for predicting O3, even if you know what O2 is. So the observations do not satisfy the Markov property, but the states do. Does anybody have any questions about this? Okay. All right, a little bit of an aside on notation. So, some of you may have studied, for example, control theory in the past, or if you've done a little bit of robotics. I'm using S and A S to denote state and A to denote action. That seems very reasonable because the word state begins with S and the word action begins with A. This kind of terminology is largely inherited from the world of dynamic programming, which was studied by folks like Richard Bellman in the 1950s. You might have seen other notation. So you might have seen, for example, the letter X used to denote state and the letter U used to denote action. This kind of terminology is a little bit more common in controls and in robotics. I will typically use this notation, but occasionally I will switch to this. Don't be alarmed by that. It doesn't really make any difference. So this kind of stuff is more common in controls, studied by folks like Lev Panteryagin. And in case you're wondering, X denotes state because X is what we use for unknown variables. U denotes action because that's also the first word in the word for action in Russian, upravlение. So similar principle. And don't be alarmed by this. They just mean exactly the same thing. Okay, let's talk about the main topic for today's lecture now, which is imitation learning. So far we've introduced some notation. We've introduced how we can have these policies. Now, how do we actually acquire policies that we can actually use to control our autonomous agents? So first what I'm going to do is I'm going to switch away from this silly tiger example to something maybe a little bit more practical, something we might be more interested in doing. We're going to use as a running example a kind of autonomous driving scenario. In an autonomous driving scenario, you could imagine that your observations are going to be images from a camera mounted on your car, and your actions, let's say, will be steering commands. So do you turn the steering wheel to the left or to the right? Don't take this too seriously. If you actually want to work on autonomous driving, you can start with some of the things I'll cover in today's lecture. It's a little bit more complicated than that. But it makes for a nice example because it's very natural for us to imagine, for example, getting example demonstrations of driving from humans and then using them to train autonomous agents. In fact, we'll actually see some example videos of people trying to do just that in today's lecture. Okay, so if we're doing imitation learning, that means that we're actually learning our policies from examples. Where can we get examples? Well, maybe we can get this fella here to drive the vehicle. We can record his observations O using a camera mounted on the dashboard, and we can record his actions A by using an encoder mounted on the steering wheel, and that gives us a data set. So it's a data set of tuples O, comma A. And now you look at this thing and you say, okay, well that's a neural net that outputs the probability of A given O. I've got a data set of A's and O's. I'm going to think back to my days of training, image classifiers and things like that, and just do kind of the obvious thing. I'll just run supervised learning and see if I can get a model, learn model pi, a policy that actually reproduces the kind of actions that I saw in my data. So here's the question for you guys. Is this going to work? Is this a good idea? Does anybody have any hypotheses? Does anybody want to volunteer a guess as to whether this will work, and if so, why, or it won't work, and if so, why not? Yes, back there.
I have some generalization problems during evaluation if you see some states that you haven't seen during training.
Right, so the answer was, well, maybe it won't work so well because you'll have some kind of generalization problem if you see some state that you didn't see during training. That could be. Any other guesses as to whether it will work or it won't work? Yes?
In this case, since we're using observations instead of states, like I know, like when we drive around, we keep in our back of our heads, like where other cars are, what's happened before, that kind of stuff. But in this case, if we're just using the current observations and trying to predict an action, it doesn't allow for the fact that it's non-Markovian.
Right, okay, good answer. So maybe it won't work because when we're driving, we don't just like see a snapshot of the world, react, and then forget everything. We actually use our memory. So if you saw a car like on your left and like in your blind spot, maybe you're not going to change lanes to the left because even though you don't see that car right now, you know it's still there. And if we're just training the policy based on the current observation, maybe it won't do that and will like hit people when it changes lanes. So that's no good. Does anybody have a more optimistic answer? I think you guys were just primed when I asked the question. It's like, well, if I'm asking the question, then surely the answer is no. Does anybody have any thoughts? Anyone have more optimistic thoughts on this topic? Yeah?
I guess if you like stack enough observation, enough long to make it like closer to the state, maybe it will work. Like
Okay.
the examples that you mentioned, if we stack all the maybe half an hour observation together to be a big vector and then try to predict,
Right.
that will work.
Yeah, so the answer for those of you that didn't hear is, well, okay, fine. It may be not Markovian, but just stack a half an hour's worth of observations together and predict the action from like a 30-minute video, and maybe then it will work. Not a bad idea. Okay, well, let's try to dig into this a little bit and see what some of the answers are. So the reason that the answer is a little tough is because actually we don't know. So so this method, by the way, is called behavioral cloning. So if you see someone say behavioral cloning, they just want to sound fancy and all they really mean is supervised learning. But this is called behavioral cloning. And does behavioral cloning work? Well, no. On this slide, I'm going to say no. Why doesn't it not work? So here's one intuitive explanation for why behavioral cloning does not work. Let's say that you have a very simple system. So I'm going to show a lot of diagrams like this in my lectures. When you see a diagram like this axis means state. Like you can think of a cartoony kind of one-dimensional state. And this axis means time. And this little wiggly line is a trajectory. So it's basically a sequence of states over time. So that you can think of this as a crude cartoon for an example demonstration. So maybe in this one-dimensional world, your human driver drove like this. And that's your training data. And now you're going to use this training data to train your policy, and then you will run your policy. Now, the thing about learning is that learning algorithms always make mistakes. They might make very small mistakes, but they're never completely perfect. Especially when you have real data, because real data inherently has a little bit of uncertainty and noise in it. So when you train on this black line, and then you run your policy, so the red line is going to denote the trajectory you get from running your policy. You know, initially, it'll be pretty good. Let's say you used a big neural net. You really know how to train that neural net. You did a good job. But it made a little tiny mistake. You can just about see it. It's like a 1 pixel big mistake. But because it made that little tiny mistake, maybe the mistake is a little bit bigger. It made a little mistake. Now it's in a situation that is just a little bit different than any situation it's seen before. That's not fatal. You know, it's okay. Neural nets can generalize a little bit. But if it made a little tiny mistake before when it was seeing something that was very similar to its training data, and now it sees something that's just a little bit less similar to its training data, it'll probably make a slightly bigger mistake. Right? It made a small mistake before. Now it's seeing something a little bit newer. Now it'll make a slightly bigger mistake. And when it makes a slightly bigger mistake, it'll find itself in a situation that's even more different from any situation it's seen before. Maybe it's still not fatal, still kind of close, but just a little bit more different. And now it'll make an even bigger mistake. And these mistakes will compound. They'll get bigger and bigger because every time it makes a mistake, it might find itself in a situation that's even more distinct from anything it saw during training. And because these mistakes will compound, eventually you'll actually make a big mistake. And we'll actually see in the second half of today's lecture that we can analyze this situation theoretically, and we can even try to understand how the magnitude of those mistakes scales with the length of the trajectory. So we'll make this much more formal later in the lecture. But for now, this is the intuition, that you make small mistakes at first, which cause you to make bigger mistakes because they put you in states that are different than states you've seen before. So that seems rather grim. But in deep learning, we never let theoretical impossibility stop us. So we can actually give this a shot and see what happens in practice. And in fact, some folks at NVIDIA gave this a shot. And it didn't work, right? So you can see this car is doing some pretty silly things. So they did what we always do in deep learning, which is they just said, let's wait for longer and collect more data, in their case 3,000 miles worth of data, and let's just try again. And after 3,000 miles, somehow things seem a bit better. That seems weird. Okay, suddenly it's not knocking down cones anymore. I still don't think it's like a really good autonomous driving system, but it's clearly better than what you were seeing before, right? It actually makes it around the cones, and they seem to actually put it on a road with other cars without killing anybody, so that seems actually pretty cool. So what the hell happened? Why is this seemingly impossible thing suddenly behaving itself? Well, there are a few things going on, and there's more than one thing, and we'll try to go through a few of these things in today's lecture. The first one is, if you actually go and check out that paper by Jarsky et al., they have this funny diagram in the paper. So they have some things that you might expect. They have a steering wheel, and they have a convnet, and they have cameras. That's kind of like the diagram I had before, except they have 3 cameras for some reason, not 1. Why do you want 3 cameras? Well, here's the idea. So you have your car, and your car has a forward-facing camera. And now, with this forward-facing camera, you might make a little mistake. You might, maybe you're following a lane, and you drift a little to the left. Now, if you remember my diagram from before, once you make a little bit of a mistake, you find yourself in a situation that's different than any situation that was present in the training data, and you might be liable to make a bigger mistake. So if you drift a little bit, you're a little to the left, maybe you'll drift even more to the left, and then eventually you'll go off the road. So what they did, which was simple and quite clever, is they also have a camera that's pointed a little bit to the left. So they're driving along, and that camera sees what the car would see if it was going a little to the left. And they take the action that the human driver took, and they bias it a little to the right, and they use that to label the image from the left camera. So now, even though the car stayed on the road, it saw these slightly leftward-facing images, which were labeled with slightly rightward steering actions. So now, if it were to actually drive using the learned policy and veer a little to the left, it sees a situation that's a little similar to what it saw from that left-facing camera during training, and will take an action to correct a little bit to the right. And the same thing for a camera that faces to the right, label it with actions that veer a little bit more to the left than what the human driver actually did. It's a little bit of a hand-designed choice, but you can kind of imagine how this might mitigate this drifting problem. Now, this is, of course, rather specific to the particular situation involving cars following lanes, but it is actually a viable solution to this drift problem. And more generally, you could imagine a setting where this trajectory that you saw for your training data is not just a single isolated trajectory, but it comes, because a single isolated trajectory will cause us drift, but it comes from some distribution over trajectories, and that distribution is produced by a stable controller. Stable meaning that when it makes some kind of mistake, when it receives a perturbation, it will correct that perturbation and recover. So maybe inside of that distribution, there are many, you can sample many trajectories from it, which all make little mistakes, they veer off to the side, but then they correct. And if you see lots of these mistakes and corrections, and you train on that, now when your policy makes a little mistake, it will actually recover from that mistake because it's seen other mistakes like it in the past. And this basic idea can be used in a variety of ways. It can be used somewhat heuristically by taking your data and relabeling with fake actions. It can be used to inform how your data is collected. So you might, for example, intentionally collect data from suboptimal demonstrators who make little mistakes but then fix those mistakes. You might artificially force them to make mistakes, so wouldn't recommend that for a driving scenario, but you could imagine someone driving the car and the car actually perturbs them, like makes them veer off to the side just to force them to illustrate the correction. Not a good idea for a car, but it could be a good idea in other settings, and in fact, there has been work that has studied this. Or later on in the course, we'll also discuss how you can do imitation learning of, not from humans, but from other controllers, and if those are stable controllers, then you can inherit their stability via imitation learning. So it's a kind of a general principle that you can use in a variety of different ways to increase the chance that your imitation learning method will succeed. Okay, does anybody have any questions about this? Yes, over there.
So, are you saying that the leftward and the rightward cameras were simulating some slight mistakes so that the distribution?
Yeah, so the question was, so were these left and right cameras kind of simulating some mistakes? Essentially, yeah. So by recording the images from the left and the right camera, they're basically capturing what the car would have seen if it had made a mistake going too far to the left or too far to the right, and then they're employing a heuristic to relabel those images with actions that would have corrected those mistakes. Conceivably, you could also imagine that you could have done this by having a single camera and actually asking the driver to intentionally make those mistakes and recover from them. Yes?
So how do they handle something like the blind spot?
Right, so the question is, how do they handle the blind spot? This issue that we had discussed previously. The answer is they didn't. Okay. Now, so far, our discussion has been, you know, a little bit vague, a little bit less mathematically precise. What I'd like to do next is I'd like to discuss a little bit more what the actual mathematical explanation for the problem with behavioral cloning really is, because that will allow us to then derive more principled algorithms that actually might inherit some guarantees on their performance. So intuitively, the explanation for the difficulty of behavioral cloning is this kind of drift problem, that once you make mistakes, you start making bigger mistakes. Let's try to make that intuition a little bit more formal. So when you collect training data, you could imagine that the observations in the training data are sampled from some distribution. We'll call that distribution P data of O. So a very kind of cartoony view of the generative process by which these demonstrations are created is that you sample an observation from P data of O, and then you sample an action from the optimal policy condition on that O. Right? So somewhere in the human driver's mind, that's sort of what they're doing. Now, of course, these O's are not independent of each other because obviously the current observation will affect the next one. But when you're doing supervised learning, you ignore all that. So as far as you're concerned, you just got some samples from some P data of O. Now you're going to use this data to train your pi theta A given O. And then you will run this pi theta A given O. Run pi theta means sample from pi theta to get the action, apply that action, and see what happens next. And when you do that, you will receive observations. But those observations come from a different distribution. They come from a distribution we're going to call P pi theta of O. Right? Because your policy doesn't perfectly match what the human would have done, and therefore it results in different observations. How different, we don't know, but they're different because you took different actions. So the trouble, of course, is that P pi theta is not equal to P data. Right? So in supervised learning, if we train on some training distribution and we have enough data, then we know that we'll do well on other samples from that same distribution. But we don't really know anything about how well we'll do on samples from a different distribution. And here, we're going to be evaluating our policy on a different distribution, specifically on the distribution of observations that that policy itself produces. And that is the root cause for why behavioral cloning, in theory, shouldn't work. So then, of course, we can ask the obvious question, well, can we make it work by somehow forcing P data to be equal to P pi theta? If we can do this, if we can ensure that our training data distribution is equal to the distribution of our observations that we'll actually see when we run our policy, then this distribution mismatch problem disappears, and in principle, our behavioral cloning policy should do very well. Okay, so does anybody have any ideas how we can do this? How can we force our training data distribution to be equal to the distribution of our observations that we'll actually see when we run our policy? Yes?
If you inject noise, it'll be more robust to shifting.
It's an interesting idea, yeah. So the idea for those of you that didn't hear is, well, maybe if you inject noise, they'll be more robust to this kind of distributional shift. One of the ways you could think about that is if you inject noise, you're taking these two distributions, you're just making them thicker. So if you make them thick enough, maybe they'll just overlap so much that they'll look similar to each other. It's not a bad idea. And in fact, people have tried that before, and you can actually make that work somewhat. Any other ideas? Back there.
Adding penalties for actions that would deviate from the observation.
Okay, that's an interesting idea. So you can try to somehow add a penalty for actions that will result in deviating from the observations that you've seen in the data. That will actually work if you can do it. The trouble is that that requires you to use a reinforcement learning algorithm. We'll actually learn about that much later on in the course when we talk about inverse RL, and that is a viable way to solve the problem, but it introduces some algorithmic complexity. There was a suggestion here. Take your
I was
time.
going to say something that wasn't really realistic.
It's okay.
Just train it on the whole population.
Yeah, just train on all observations and states you've ever seen. That will actually fix the problem, yeah. In fact, the solution I'm going to present next is also not very realistic, so it's okay. Yes?
Have some training data near the observed trajectory.
Yeah, so this is an interesting idea. What if you add some more training data next to this red thing, right? So I was complaining that the red stuff, that's p pi theta of O, is different from p data. Well, what if we just ask for more data in the neighborhood of this red thing, right? So basically change our p data to make it closer to p pi theta. Like you can, for example, ask a person to drive the same way that the computer drove. You can actually do something like that, and that's more or less what the algorithm I'm going to describe next does, although in a slightly more elegant way. So the idea in this algorithm will be that we won't actually change the policy so much as we'll change the data. So instead of being clever about how we train our policy, instead of imposing some constraints on it, let's be clever about how we collect our data. So this is an algorithm called DAGGER, which stands for dataset aggregation. And the goal of this algorithm is to collect training data from p pi theta instead of p data. Because if we can do that, then we'll be training on the same distribution as we'll be testing on. So how do we do that? How do we collect data from p pi theta? Very easy. We just run our policy. Because when we run our policy, we're sampling observations from exactly the right observation distribution. The problem is that we need to label those observations. So here's how it's going to work. Step 1, train your policy on human data. Now this policy will not necessarily be very good. So this step 1 is literally just like run behavior cloning. No good yet. Step 2, run your policy to get a data set d pi. And this is a data set of observations. You're going to throw out the actions because those actions are bad actions anyway. Just keep the observations. And then you're going to ask a person to go through all these pictures and label them with actions. And if this sounds a little bit silly, it's because it is a little bit silly, but you can kind of imagine that you're sitting in a really boring driving simulator where you actually just see videos of somebody else driving and you just ask to turn the steering wheel the way that you would have done it. And then you're going to aggregate. You're going to basically merge d pi and your old d, and then go back to step 1 and retrain. And you'll do this over and over again. So each time through this loop, you're going to collect some data from your latest policy, ask a person to label that data with the optimal actions, retrain on that data, and repeat. Fairly simple algorithm. The person here is not actually driving the car except for the initial data set. They're just looking at the computer driving the car and telling the computer what they would have done in that situation. And you can actually prove that this procedure will bridge this distributional shift problem, and we'll actually discuss that later in today's lecture. But for now, let's see a video of this in action. So here is DAGGER flying a drone. So this is a drone that was trained with multiple iterations of DAGGER. The action is shown at the bottom. It's a scalar value indicating how much you should go left or right, and it's using vision to fly around some trees. So the initial policy was not very good, and then it went through multiple iterations of receiving these additional human labels. Okay, what's wrong with this thing? Does anybody have any ideas or suggestions or thoughts about what might be a problem with this algorithm? Yeah?
Getting humans to label large data sets, especially expensive.
Can you say that again?
Getting humans to label data sets, especially large ones.
Right, so getting humans to label large data sets. That's generally kind of a tough thing, and you have to do it iteratively. So you have to do it as you train your methods. So you can't just get a data set in advance and then just train multiple different models on it, because the observations depend on your model. So you have to keep recollecting data and relabeling it. Over there?
There is no continuity in the action.
Yeah, so to rephrase this, you're kind of asking people to do something pretty unnatural. You're asking them to label these observations with actions, but people kind of, they rely on some degree of temporal continuity, of temporal coherence. So when you're driving a car, it's not like every single time step is a separate snapshot. You know, you're holding the steering wheel like this, you'll probably be holding it the same way at the next millisecond. So this mode of asking people to provide labels, in some cases, can be quite unnatural, and they might not provide good labels. Any other suggestions? Yeah?
If your initial policy is like extremely unrealistic, then the data you generate from that will also be extremely unrealistic and not match the real world.
Yeah. So you could, for example, have a car that, you know, it's trained in step 1, and in step 2 it drives off the cliff, and then you have no more car. And now it's going to be very hard to keep training this system. Now, you can actually show theoretically that if you do this enough, eventually this problem is solved under some mild assumptions, and those assumptions are not actually all that mild. Like, for example, they assume ergodicity, which means that you can always come back to where you started, which is not true if you go off a cliff. But that is, in practice, potentially a major issue. So your initial policy in step 2 can't be that bad. Otherwise, you'll just be collecting pure garbage. Any other comments? All right. So yeah, one thing that I thought of as I was making this slide that was bothering me a lot is that this step of asking a human to label these observations kind of seemed a little tough. Like in some cases I can do it. Like for example, if, I don't know, you're using this to like play chess, people can probably do a pretty good job of looking at a chessboard and figuring out the chess move, even if they're not controlling the chess game. But if they're like driving a car at high speed, maybe that's a little tricky for them to do. Okay. Can we make behavioral cloning work without asking humans for more data and without putting additional cameras on things and stuff like that? So theoretically, the answer is no. And what does it mean when I say theoretically the answer is no? What I really mean is that you can construct a counterexample, a pathological situation where it will not happen. But of course, the real world doesn't consist exclusively of pathological situations. And in real world situations, sometimes you can actually make it work. So let's discuss a few practical considerations that can help us make behavioral cloning work in practice, even if there are no guarantees. So Dagger addresses this problem of distributional drift, distributional shift. But this distributional shift occurs because our model makes mistakes. What if our model is so good that it hardly ever makes any mistakes? It's not actually as unreasonable as it might sound. So if your data has a little bit of noise to it, meaning that it illustrates a little bit of stability, and your model is very, very powerful, maybe you can actually get a model that hardly ever makes mistakes that are so big as to actually cause these compounding errors. And in practice, in some situations, you can actually get that to happen. So you need to mimic the expert behavior very accurately. And there are a couple of things that we need to take into account in order to do that successfully. And you also need to not overfit, because obviously if you overfit, you won't do a very good job. So why might we fail to fit the expert? If we can answer that question, then maybe we can address each of those issues and get models that hardly ever make mistakes. So what are some reasons why a learned model might not mimic the expert's behavior very well? Any ideas? Some of them have come up before in the discussion. Yeah?
Maybe the observations are not very good.
Right, so maybe your observation space is just kind of impoverished and you just can't figure out what you're supposed to be doing. So the example before about needing histories, for instance, that's an example of an impoverished observation space. So maybe we can address that. Any other thoughts? Yeah? Multimodality, right. So it could be that humans are not actually very consistent. Maybe in the same situation they might do a few different things for seemingly arbitrary reasons, and maybe your model has trouble capturing that. So I'm going to talk about the two things that I found to be the most problematic, which are non-Markovian behavior and multimodal behavior. And I'll talk about each of these issues and some of the things we can do, some ways we can modify our model to make it better at handling these. So let's start with non-Markovian behavior. Okay, so formally what this means is the following. Our policy is a distribution of our actions conditional on the current observation. But so what this implies is that if you see the same thing twice, you're going to do the same thing regardless of what happened before. But this is often very unnatural for human demonstrators. So if you're like driving a car and maybe somebody just cut you off, now maybe you'll be like a little bit more cautious for the next like 30 seconds because you're a little scared or something. But more kind of a simpler situations, you're a little lazy. Like if you just turn the steering wheel to the left, you'll probably keep it turned to the left for a little bit, even if maybe the optimal thing is to suddenly immediately straighten it out. So people have a little bit of inertia, a little bit of kind of hysteresis in their behavior, and it's very kind of unnatural for people to act in a truly Markovian way. Partly because we have bounded rationality, we don't sort of think through all of our plans instantaneously every single millisecond, and partly also just because of the physics of the environment that we inhabit. So maybe a better model might be something that produces a distribution over the action conditioned on a history of past observations. Because if you do that, then you can account for these patterns. So the behavior might depend on all past observations. Now, this is very easy to write down on a slide like this, but in order to actually implement this, you have to do a little bit more work. Because if you want to do this, very easy. You just set up a convnet, output the mean and variance of a normal distribution or a softmax over discrete actions. Very easy to set up. Train this in your favorite deep learning package. It will just work. This is a little more complicated. So how can we incorporate the whole history? Well, a very straightforward and naive way to do this is to simply take your history of observations, concatenate them into one gigantic observation, and feed that through your model. If you have a very short history, maybe 5 time steps, or you have a very small observation, so maybe it's not an image, but it's like a vector with 5 numbers, then this is pretty straightforward to do. But if you have very large observations like images, or a very long history, then this kind of model will not work very well because you'll have a really gigantic input, which means you'll have a very large number of weights in the first layer, which means that you are liable to overfit. So maybe you have a variable number of frames, or maybe they're just too big, you might have too many weights. So a better model, and something that people do often use when they want to deal with non-Markovian observations, is to use a recurrent model. So in a classic kind of recurrent model with image observations, you might have an encoder with shared weights, so some kind of convnet that takes an image and encodes it into some relatively more compact non-convolutional representation, and then some sort of RNN unit. You can also use things like temporal convolutions, but RNNs are a good starting point. Typically, the simplest thing to do to make this work is to use an LSTM cell for your RNN, use a shared encoder for a convnet, train it using your favorite deep learning package, and then you'll get a model that can ingest history. I won't go into the nitty-gritty details of training LSTM models like this, although if you do want to try that out, for example, as something of your own initiative on homework 1, you can feel free to stop by the TA's office hours and get them to help you out. But this is kind of the basic scheme for a model that handles non-Markovian observations. Does anybody have any questions about this? Or does anybody have any thoughts about what might go wrong with these kinds of models? Okay. Yes?
Wouldn't that be like really computationally expensive to do something like that?
Wouldn't be computationally expensive. Yeah, so it could be kind of expensive. So for example, maybe you're driving the car and you want to output a new action every like 10 milliseconds. Running through a forward pass through the whole RNN in 10 milliseconds might be hard. At runtime, you can do some tricks. You could, for example, cache the state of the RNN. So you can basically not recompute all of this part, just append another observation down to the bottom, and that can speed it up implementation-wise. But yeah, both for training and for evaluation, RNNs can be a bit more expensive. There's kind of a more fundamental issue. This is a little bit of an aside, like this is kind of not the main topic of the lecture, but I wanted to bring this up because I think it's kind of cool. There's a subtle reason why more sophisticated models, especially models with history, can actually work poorly in a behavioral cloning setting. So I'm going to illustrate this with sort of a silly example. It's silly because real cars don't actually work that way. But let's say that you're driving this funny car that has a brake indicator on the dashboard. Okay, your car probably has like a turn signal indicator. This car is a brake indicator. So when you step on the brake, there's a light that lights up on the dashboard. I know that real cars don't have this, but it's not too hard to imagine. So now your camera sees the brake indicator and it sees the stuff outside the windshield. And every time you press on the brake, the light goes on. So what's the model going to learn? Well, it can learn one of two things. It can learn something pretty complicated, like if there is something in front of the car that indicates that it should stop, like a person or a stoplight or a deer or whatever, then it should step on the brake. Or it could learn something much simpler, which is when the light turns on, step on the brake. And it will definitely learn that one, because that one is way easier. So of course, that's kind of bad news, right? Because the light turned on because you stepped on the brake, not the other way around. But if these events happen instantaneously, it's very hard for the model to tell the difference between these things. If you were to like blank out the dashboard, then obviously this wouldn't happen. But now let's think about what this has to do with history. So here, if you don't have history, the events basically have to be instantaneous in order to be correlated like this. If the brake light only turns on like 5 seconds after you press on the brake, then there's no problem. But if you have history, then your model can actually correlate your action with things that happen at some point in the past. So for example, you're stopped at a stoplight. It can say, well, If you've been stopped at a stoplight, you should step on the brake because you're stopped at a stoplight. It can say, well, if there's like a car, maybe you have a rear-facing camera and sees, oh, if there's a car behind you that's slowing down, you should slow down too, because in the data, whenever you slow down, someone behind you slowed down, and it can't tell which way the causality goes. So history tends to actually exacerbate this problem. History creates versions of this problem all the time. We've kind of termed this the causal confusion problem. If you want to learn more about it, there's a paper called Causal Confusion in Imitation Learning that describes this phenomenon. So does including history exacerbate causal confusion? I guess I've kind of answered this. The answer is it actually tends to exacerbate it. Here's a second question. This is a question for you guys. Does Dagger actually mitigate this problem? Like if you do this thing where you let the policy drive and then you label the data with a human expert and then you append that data and then you train on it, will it fix things like that brake indicator problem? But you'll have to give me a reason. So you have to like raise your hand. Yes?
Maybe because neural nets are so over-parameterized that they can learn, like, I guess both that it'll just be confused.
You think it'll be confused? Okay. Any other hypotheses? Yes?
If it learns a wrong policy the first time, then it might reinforce that policy if you keep adding data from running that policy to the original.
It might, yeah. So theoretically, I don't know the answer. Empirically, the answer appears to be that it does seem to fix it. Theoretically, I strongly suspect the answer is that it does fix it, but I don't know that for sure. But maybe to share a little bit of intuition about this, you know, if it is something like this brake light situation, what will happen is that your policy will drive around. It will fail to step on the brake in cases where it actually hits the pedestrian, and presumably the human expert will go in and label those as states where you need to step on the brake. So you'll basically get more data where the brake should have been pressed but the light was not on. But I don't know theoretically whether this will fix all instances of this problem. It appears empirically to fix it. Yes?
I have a question regarding the Dagger.
Mm-hmm.
You were mentioning like when human labeled once again, human only labels like an 01 through like 08 or something. Does human look at just the one image, or do they have history as well?
Right. So the question for those of you that didn't hear is, in Dagger, when you ask a person to label the image with the action, does the person get to look at the whole history or just the current observation? So theoretically, what you should do is you should show the person exactly the same thing that the model would have seen, because you want them to make the decision based on the same inputs. In practice, it's sort of a matter of how you implement the system. So for that drone flying example, the way that that was done is that people were actually given a video from the drone, and they were basically given a pause and play button. So they would advance a frame, figure out where they want the drone to go, advance, figure out where they want to go, and repeat. So there they obviously knew the history. But in theory, it should be independent. Okay. So that was non-Markovian behavior. Let's talk about the multimodal behavior a little bit. So what is multimodal behavior? Well, here's my favorite canonical example of multimodal behavior. You want to fly the drone around the tree. This is good, and this is good. But average those two together, and it's bad. So, okay, is this actually a problem? Well, if your actions are discrete, so you're outputting a categorical distribution over a discrete action, and maybe there's like action 1 is left, action 2 is middle, action 3 is right. That's not a problem. You can easily output a distribution that gives 50% left, 50% right, and 0% to go straight. So there's actually no problem. But if your actions are continuous, and you weren't careful in choosing the parametric form for this distribution, maybe you chose a normal distribution for your action, now you would have exactly this problem, because if half your data goes left and half the data goes right, the maximum likelihood normal distribution fit to this is to go straight, to basically average the two modes. And that's bad. So that's basically like this situation. This is what the model thinks will happen. Okay, so there are a few choices that you have. One choice is to not use, well, they all actually correspond to not using a single normal distribution. One is to use a mixture of Gaussians. It's sort of, in some ways, maybe the least elegant, but it's the easiest to implement, and it tends to actually work decently well. The second one is to use a latent variable model, and I'll go into a little more detail on each of these. And the third one is to use what's called autoregressive discretization. And among these three, I will kind of tell you that like number 1 is easiest to implement, number 2 is theoretically kind of cool and elegant, but kind of a pain to implement, and number 3 is kind of a nice balance between being fairly easy to implement and also very expressive. So kind of 3 is sort of a compromise solution. Okay, so output a mixture of Gaussians. What does that mean? Well, it kind of means the obvious thing. Instead of outputting the mean and variance of a single normal distribution, you actually pick, let's say you're going to output n different normal distributions. So you output a mean and variance for each one, and you output weights on each of the n. So your output distribution is this mixture, and you're going to output the w's, the mu's, and the sigmas. So now you're outputting a lot more stuff, but you can represent multiple modes. Now, the trouble with this, of course, is that you can only represent n modes. So obviously, if you have a really humongous action space, this might not work so well. But it's very simple to implement, and actually tends to work decently well in practice. Latent variable models. So latent variable models can, in principle, be as expressive as you want, but they're a bit harder to train. So the way that you would do this is you would provide, instead of changing the output of the network, you would actually change the input. So you would have some additional variable, which has some prior distribution on it. Maybe it has a 0 mean unit variance normal distribution on it. You will sample that variable randomly from the prior each time you want to evaluate the network, and you will feed it as input into this model. Now, implementing a model like this is not too hard. What's hard is to actually train it so that it uses this additional random number effectively in order to represent multiple different modes. We'll actually discuss in a lot more detail how to train models of this sort much later in the course when we talk about variational inference. But if you want to try this right now, I'll just give you a few keywords that you can look up if you want to get ahead of the game. So if you want to learn about latent variable models, you can look up conditional variational autoencoders, normalizing flows, or Stein variational gradient descent. So these are 3 different methods that might allow you to train models of this sort. And we'll talk a lot more about the first one, variational autoencoders, later on, probably in the second half of the course. Okay, and the last one is autoregressive discretization. So this is kind of an interesting idea. If you have a very, very low-dimensional action space, even if that action space is continuous, you can turn it into a discrete action space. So if you have just one-dimensional action, the orientation of the steering wheel, it's not too hard to just separate it into lots of little bins and just make it a discrete action space. That's pretty straightforward. The problem is that if your dimensionality as the dimensionality of your action space increases, the number of bins that you need is going to increase exponentially with the number of dimensions. So in general, discretizing high-dimensional action spaces like this is not practical. So autoregressive discretization is a trick that you can use to get around this problem. The idea is the following. We're going to basically solve the problem of exponential blowup using neural nets. So what we'll do is we'll discretize one dimension at a time. So let's say that your action has 5 dimensions. We'll take the first dimension and we'll split it into a bunch of little bins. Here I have only 3 bins, but in practice you probably use more than that. And we're going to have a softmax over those bins, so a categorical distribution. And then what you would do when you evaluate the network, when you run it forward, is you would sample from that softmax, so that's a discrete sampling operation. That gives you a value for the first dimension of the action. And then you feed that value as an input into another neural net. You could actually have shared weights, in which case it becomes a recurrent network. But don't worry about that too much. So you'd feed it into another neural net. This neural net in general will probably take in the image and this first dimension, and it outputs a discretization over the second dimension. And then you sample from that, and then repeat the process. So this way you sample one dimension at a time. You never have to discretize the whole action space. You only have to discretize one dimension of the action space at a time. So you're always only discretizing one-dimensional things. When you train this, you simply, you don't even do the discrete sampling. When you train this, you simply put a cross-entropy loss on each dimension. And that works. So it's a little harder to implement because you have to change your architecture to put in these little mini neural nets to read in each dimension. But it allows you to represent very complex distributions, discretizing only one dimension at a time. OK, any questions about this or any of the other multimodal solutions? All right. So to briefly recap what I covered so far, behavioral cloning, it's often but not always insufficient by itself because of the distribution mismatch problem. Sometimes it works well. There are some things you can do to increase the chance of it working well. You could, for example, use hacks. like putting camera that faces left and camera that faces right. You could sample from a more stable trajectory distribution. So you could, for example, intentionally ask your human expert to make mistakes so that they can correct them. You could add more on-policy data, for example, using Dagger. Or you can just design a really good model that fits your data very well. So in practice, that last one can actually work decently well. In theory, you really need to do something like data aggregation to really guarantee that the distributional mismatch is fully resolved. OK, so at this point, what I'll do is I'll take a 2-minute break. So we'll be back at 11:12. And then we'll conclude with a little bit of a discussion of some case studies and maybe a little bit of theory if we have time for it. So see you in 2 minutes.
You know when the notes will be sent out if you got an email saying that you were going to be enrolled in the course?
We're probably going to try to do that today. The main challenge there is we have about 170 numbers to send out, so it's a lot of emails for our TAs to send.
And then how long are we going to have to add the course? Because I'm processing to get this class accepted for the EECS requirements right now.
We don't really impose any time limit. We'd kind of appreciate if you figure it out in like a week.
Oh yeah, they said they'd give me the form back within the week.
Okay, if you need more time, just when Anusha sends you the code, just let her know that you're going to need a little longer, and that's
Okay.
it. Yeah.
Thank you.
Do you have a question?
Just a quick question. Your office hours are today from 11:30 to 12:30?
340. Yeah, in room 347.
347?
I'm just going to go there right after class.
So like my research class not like technically aligned with reinforcement learning, but they use some concept like autobiographic and also like meta learning. Is it possible like just use some like concept learned from this lecture in project, but it's not like technically robotics?
Well, why don't you come talk to me or to one of the TAs in office hours, and maybe we should discuss the specifics a little bit. So it kind of depends on the details.
Okay, thank you.
All right, folks, I'm going to restart shortly, so please have a seat. Okay, so I had attempted to time this break to be in the middle. As you might have noticed, I'm running a little over, but that's okay. So what I want to do next is I want to tell you a little bit about some research that people have done that makes use of imitation learning to do some cool stuff. And then I think I'll have time to dig into a little bit of theory. And if I don't get through all of that, then I'll conclude that on Monday. But first, let's see some cool videos. So what I'm going to show you next is a video from a paper that uses behavioral cloning to fly a drone through woods in Switzerland. I imagine it might also work in woods in other countries, but this one flies in Switzerland. And what I want you to do is, as you watch the video, try to guess how they made this work. And then the answer will be revealed to you towards the middle, and you can see if your guess is correct. So let's see this in action. Okay, so their goal is to get this quadrotor to fly along a forest trail. And forest trails are a little bit ambiguous, although I guess in Switzerland they're kind of nicely manicured and beautiful and so on. But you know, there's a little bit of ambiguity. You don't quite know whether it's a trail or just an opening between the trees. And you know, it's a drone, so it's going to be wobbly. It's going to be a little bit noisy. And they want to train it with imitation learning. And they're going to use a big convnet, so they need lots of data. Drones have relatively short battery life, so flying a drone for hours and hours is actually pretty hard. Okay, so now they're going to probably tell you about their awesome convnet. Okay, so here are some pictures of forest trails. their action space is actually discrete. It's just left, straight, or right. So here they're going to tell us how they solve the problem. Okay, so discrete action space, left, straight, or right. And the model will predict one of three classes. So it has a little softmax layer at the top. It is going to take in images. Can you guess how it's going to be trained? Well, first, this part is the obvious part, right? It's a convnet, so they're just showing you the different filters in the convnet. Yes, it has many layers and many weights, as all convnets should have. That's good. So now we got to train the classifier. We call it a policy, but they call it a classifier. With lots of data. That's what training looks like. Any guesses where they get the data? Any guesses now? All right, so now you've hopefully figured it out, right? So this one is labeled as right, this one is labeled as left, and this one is labeled as straight. So it's sort of it's a little bit like the NVIDIA thing, only arguably like even more kind of clever, because they don't actually even have a person flying a drone. They just have a person with a really stylish headband. You know, could have been just an excuse to do a little bit of extra hiking through the woods. But it turns out, you know, it's actually a great way to collect lots of data. And if you can collect lots of data, then you can get a better policy out of it. You get 20,000 images. So actually not a single one of the images actually comes from an actual drone. Okay, so from here you can kind of use your imagination to figure out the rest. So you can do some pretty fun things, and this is like a fairly easy thing to do if you want to try something like this at home. Okay, so that's maybe a little bit of a glimpse of how things like this can work in practice. But let's kind of step back a little bit and think, well, what's kind of the problem with imitation learning in general, like more globally? Why do we need the rest of the course? Why can't we just stop at today's lecture and just go with what we've learned so far? Well, for imitation learning, you need to have humans provide data, and this data is typically finite. And the trouble is that deep learning really works best when data is very plentiful. In fact, generally, the more data you have, the better your model will work. And that's why those guys needed to put the cameras on a person's headband instead of on a drone, because they get way more data from having a person walk around in the woods than have a drone flying around in the woods. Humans are also not good at providing some kind of actions. So humans are pretty good at walking along forest trails in Switzerland, and they're even good at flying drones sometimes. They're not so good if you ask them to actually directly specify what the voltage on all the motors in the drone would be. That would be a little harder for a person to do. And if you ask them to control all the degrees of freedom of like some giant humanoid robot, or to control all of the degrees of freedom of a warehouse managing inventory for Amazon, now those things might be a bit harder. And in those settings, maybe you'd like to actually have machines that learn from their own experience rather than relying on human data. So then there's also kind of the more conceptual qualm that we might have, which is that humans are actually pretty decent at learning autonomously, and it kind of seems like maybe our machines should be good at it too. Maybe we shouldn't have to rely on being led by the hand for all the things that our machines need to figure out. If they can learn autonomously, they can get unlimited data, in theory, from their own experience, which could allow them to build very, very big models that will generalize very well. And they can maybe continuously improve themselves from their own experience. So it seems like it would be really nice to get beyond just following example data, to actually learn how to solve tasks on your own. So let's modify our terminology a little bit to give us at least the definitions that we need to start thinking about learning without imitation. So if we come back to this picture, back to the lion and your continuous actions to run away from it, you might say that, well, what you really want when you're faced with this is not to imitate somebody's actions, but to like minimize the expected number of times you're eaten by the tiger or something. Like, this is a delta function. This function is 1 if you're eaten by the tiger and 0 otherwise. It's a function of your next state S prime. Your next state S prime is distributed according to P of S prime given SA. Your A is distributed according to A given S. And you're just saying, like, find me a policy such that this expected value is small, which means that in expectation, you're not going to get eaten by a tiger. So this is an overly mathematically complicated way to say, do the thing that doesn't get you eaten. Now, in general, you might prefer not to get eaten by the tiger today and tomorrow and the day after. So you could write it like this. You could say, I want to minimize the expectation for a sequence of states and actions of this delta function for being eaten by the tiger. And this is getting closer to what a proper reinforcement learning problem looks like. So then just replace this delta with some cost, and then you say, well, what I really want to do is I want to minimize the sum of these costs over a time sequence, and the states are distributed according to the dynamics, and the actions are distributed according to the policy. And we'll make this much more concrete and much more detailed in the next lecture. So now we have to introduce a couple more objects. So we have states, observations, and actions so far. Now we have this thing called the cost function. So it's just a scalar valued function of states, in general states and actions, although often it's a function of only states. So the cost gives you a numerical quantity of how bad things are. So getting eaten by a tiger might have a cost of like 1 million. Getting bitten by a mosquito might have a cost of 1. Or you could equivalently write things in terms of rewards. So you could say, well, costs are things you want to minimize, rewards are things you want to maximize, but they really mean the same thing. It's just whether you put a max or a min in here. So as an aside for notation, this is the same kind of historical notational quirk as before. In the world of dynamic programming, typically we have states, actions, and rewards. In the world of optimal control, we have states, actions, and cost functions. They really mean the same thing. The reward is just the negative of the cost. Why costs versus rewards? I don't know. I have a personal theory, which is that this stuff was pioneered in the United States. This was pioneered in the Soviet Union. So maybe, kind of use your imagination. Slightly different national mindset. Okay. But don't be alarmed by that. The thing that I want to talk about today, though, to sort of round out our discussion, is to tie back this notion of costs back to imitation learning. So in some ways, costs and rewards maybe provide us with a more general way to specify what kind of behavior we want. Can we actually define a cost function or a reward function for imitation learning and study the degree to which imitation learning algorithms actually optimize that cost or reward? So in imitation learning, as you recall, we have this, somebody providing us with actions for their observations. That's our training data. What if we define a reward function as the log probability that your action matches the action from the optimal policy? So if you assume for a minute that this person has a deterministic optimal policy, so he always picks the very best action for the current state, you could imagine saying that your reward is to maximize the probability of the right action. You might not know what the right action is, but you have a bunch of data to help you figure it out. You can also use an even simpler reward or cost. I'm going to write this as a cost because it's a little bit more natural. You could just say that your cost is 0 if you matched the optimal action and 1 otherwise. So it's a 0-1 loss. This one is a bit more convenient for theoretical analysis because it literally just counts the number of mistakes. So it's just saying an optimal imitator is an imitator that makes the fewest possible mistakes. A mistake is just a situation where you took an action that is not the action that the person would have taken. Now this, of course, assumes that the person takes actions deterministically. In general, they might not, in which case you might use something like a KL divergence or a cross entropy. But for now, let's just assume that the person is deterministic. OK. So what I want to start doing now is to try to analyze a little bit this dagger algorithm that we saw from before. And what I'm going to do is I'm going to analyze the degree to which it actually optimizes this 0-1 loss. Now the important thing here is you don't just want to know how many mistakes you make on the training data or even on validation data. You want to know how many mistakes you make when you actually run the policy in the real world. So this is different from how we do, for example, the validation error in supervised learning. We're not looking at how many mistakes we make on the training distribution. We're looking at how many mistakes we make on the policy's own state or observation distribution. So let's get started on this analysis a little bit, and let's try to sort of build up our repertoire of tools for doing this sort of analysis. So before we had the intuition. The intuition was that you get this kind of drift. You make a little mistake, you go to a slightly different state, you make a bigger mistake. So how bad is it? How many mistakes do you make? The length of this trajectory, we're going to call it capital T. And the mistakes are quantified by this cost. So the cost is 0 if you took the right action and 1 otherwise. Now, when we analyze this kind of stuff, what we really want is we want bounds. We want to know, in the worst case, how you'll make no more than this number of mistakes. Because in the best case, who knows? Maybe you have an action space of size 1 and it's impossible to make a mistake. Nobody cares about the best case. They care about the worst case. So what's the worst case? Well, we may need to make some assumptions. First, let's assume that supervised learning works, meaning that you can actually train your model. There are a few ways to formalize this assumption. I'll do it in a very naive way here, and then I'll do it in a less naive way on Monday. But the naive way I'm going to do it is I'm going to say that your probability of outputting an action that does not match the optimal action is less than or equal to epsilon if that state is in the training set. Now this damn well better be true, because this is not even saying in the training distribution, it's literally saying in the training set. So if the state is in the training set, you have no more than epsilon probability of making a mistake. This basically amounts to saying, like, you know how to import TensorFlow and you know how to set up a neural net with lots of hidden units. So this really better be true, although sometimes it's impossible for this to be true. It's impossible for this to be true if, for example, the state is insufficient to infer the action, like in the non-Markovian case. But we need this assumption, because if we don't assume this, we've got nothing. So you've got to assume that you can at least avoid mistakes on the thing you trained on. Okay, so what's the worst thing that could happen under this assumption? Well, the worst thing that can happen is this. What is this? This is a person doing something perhaps somewhat inadvisable. Certainly inadvisable if you're an imitation learning algorithm. This person is walking on a tightrope. And walking on a tightrope is difficult because if you make a mistake, which has probability epsilon, you will fall off the tightrope. Now, this guy doesn't like to fall off the tightrope because, for the obvious reasons. An imitation learning algorithm doesn't like falling off of a tightrope because when it falls off the tightrope, it incurs a loss. It incurs specifically this 0-1 loss because it doesn't know what to do when it's fallen off the tightrope. So here's the environment. This is a sort of a much cartoonier version of that tightrope walker. You have some states in the middle. These are the good states. This is your rope. You're supposed to walk along the rope, always go to the right. And these red states, I just colored them red. This denotes that you fell off the rope. And when you have no data there, so once you fall off the rope, you don't know what to do, and you can never get back to the rope. You just kind of keep falling. So you're not concerned about falling off the rope because you think it'll hurt. You're concerned about it because you don't have any data. You don't know what to do there. All right. So now what we want to do is we want to bound how many mistakes you will make under this assumption in the tightrope walking domain. So how do you do this? Well, first, you're going to start at the beginning, and you're going to say, what's your probability of making a mistake on the very first time step? So we want to bound this quantity, the total cost. So that total cost is a sum over all the time steps. We'll start with the first entry in that sum. What's the probability of making a mistake at the first time step? Just call it out. Call it out louder. 2/3. Epsilon. Right. So with probability epsilon, you make a mistake. If you make a mistake, you go here or here. After you've made that mistake, you can never get back. And you are always in a state that was not in your training set. When you're in a state that is not in your training set, you have no guarantees about avoiding mistakes. So in the worst case, you will actually make a mistake every single time after you've fallen off. So if you fall off on time step 0, you have capital T more time steps to go. So you have probability epsilon of making that mistake, and after you made that mistake, you get capital T mistakes after that, because when you're in that red thing, you just keep making mistakes. You don't know what to do there. So on the first time step, you can make a mistake with probability epsilon. You get an epsilon times capital T cost. And then the other term is going to be 1 minus epsilon. That's if you didn't make the mistake. So it's going to be 1 minus epsilon times the probability that you make a mistake at the next time step times capital T minus 1, because that's how many you've got left. And you keep going like this. You keep doing 1 minus epsilon times epsilon T minus 1 plus 1 minus epsilon times T minus 2, and so on and so on and so on. Okay. Now, when we're writing down bounds, we don't like to have huge sums like this, so we want to simplify it a little bit. We're going to simplify it like this. Epsilon is small, so 1 minus epsilon is big. So you can kind of say 1 minus epsilon is roughly on the order of 1. And if you have a sum that looks like t plus t minus 1 plus t minus 2 plus t minus 3, etc., 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 that's of course on the order of t squared. Right, you can imagine drawing the triangle. The area of the triangle is 1/2 of t squared. So you have capital T terms, each of which is on the order of epsilon times t. So that means that the bound that you've got here is O of epsilon times t squared. And that is very, very bad, because that means that the longer your trajectories get, the more mistakes you make, and your mistakes go up quadratically. That's bad news, because if you're training a policy, you're probably interested in temporally extended decision making. You don't just want to make a good decision right now, you want to make a good decision for a period of time, and now the number of mistakes goes up quadratically with the length of that time period. So even under these very silly assumptions, behavioral cloning actually, in theory, does very badly in the worst case. Okay, so I'm going to conclude the discussion now because I'm out of time. I will come back to this probably at the beginning of lecture on Monday before Kelvin dives into his tutorial to do this under less naive assumptions. And maybe I'll show some videos then too. So I'll see you all then. And I have office hours now in 3:47. Yeah.
For the causal confusion problem, do you have any idea how many human labels they needed to quote fix the problem?